The tunneling effect is the quantum mechanical phenomenon in which the particle having energy less than the height of energy barrier crosses the barrier. Let's try to understand this with an example. Suppose Mr. X is standing in front of McDonald's. Let's say the precise location of Mr. X is 5 meters away from McDonald's. Now let's assume that we are in a quantum world, and the dimension of everything around us is in nanometers. In this case, it's very difficult to say the exact position of Mr. X, because in quantum mechanics, every particle is located based on its probability. So instead of saying Mr. X is located 5 nanometers away from McDonald's, we will have to say the probability of finding Mr. X is maximum 5 nanometers away from McDonald's. However, Mr. X can be present either 3 nanometers or 7 nanometers away from McDonald's. It's just the probability. Now based on this, let's try to understand the quantum tunneling effect. Let's say Mr. X is trapped in a well 10 meters deep. Now the well is so deep, it's impossible for Mr. X to reach on the top of the well. However, the scenario will be different in quantum mechanics. Let's say the depth of the well is 10 nanometers. In this case, because location of Mr. X is given by probability, Mr. X will have some probability to reach on the top of the well. And this phenomenon is known as the tunneling effect. That is, Mr. X having energy less than the height of energy barrier crosses the barrier is called the tunneling effect. So the scanning tunneling microscope is based on this phenomenon. The scanning tunneling microscope has a small nano-sized tip which comes very close to the sample. When electric potential difference is applied between the tip and the sample, the electrons from the sample are tunneled to the tip. The small electric current produced by the tunneled electrons is amplified and sent to the computer. Based on the recordings of the tunneling current, the information about the surface of the specimen is known. The magnitude of the tunneling current obtained depends on the distance between the tip and the sample. The tunneling current is high when the distance is less, and the tunneling current decreases as the distance between the tip and the sample increases. The scanning tunneling microscope gives magnification of around 100 millions and resolution of around 0.1 nanometer. It allows imaging of surface at atomic level and also provides a three-dimensional profile of the surface. And the inventors of scanning tunneling microscope were given a Nobel Prize in the year 1986. Okay, now let's talk about atomic force microscopy. The atomic force microscope was invented in 1986 with a modification in scanning tunneling microscope. The atomic force microscope works on the principle of attractive and repulsive forces at the atomic level. If two atoms are located at a certain distance, then the positively charged proton of one atom will attract the negatively charged electron of the other. If two atoms come very close to one another, then the electrons in the outer shell of both the atoms repel each other. The atomic force microscope uses a small nano-sized tip, which can be either attracted or repelled by the atoms present in the sample. The earlier versions of atomic force microscope employed the use of scanning tunneling microscope tip, which recorded the oscillation of the cantilever based on the tunneling current obtained. However, it was later on replaced by a laser and a mirror, which would record the oscillation of the tip. As the cantilevers moves up and down depending on the sample surface, the laser is deflected and gives information about the sample surface. There are three main modes in which the atomic force microscope is operated: contact mode, non-contact mode, and the tapping mode. In contact mode, the distance between the probe and the sample is kept very less, As a result, the cantilever is repelled. The resolution obtained by this mode is very high. However, because of the short distance, the probe may collide with the sample and damage the sample. In non-contact mode, the distance between the probe and the sample is kept large. As a result, the cantilever is attracted. The resolution obtained is low, however, the sample is not damaged. In tapping mode, the distance between the probe and the sample is kept intermediate. As a result, the cantilever oscillates. The resolution obtained is better than non-contact mode.